Hi guys, it's your science teacher here back with another video. This time I'm going to go through the whole of the unit chemical analysis. There is some parts of this video that are triple only, so what I'll do is when I get to them parts I'll say combined students, you don't have to watch anymore, and you guys will be done. So without further ado, let's get started with today's video. So the topic of chemical analysis is all about finding what is inside of different mixtures. And the first thing in this topic is we learn a key word about a particular type of mixture, which is a formulation. And a formulation is just a mixture designed as a useful product. Now, the key thing about formulations is that each component inside a formulation has a particular job and is in a particular amount. Now down here I've got some examples of some different formulations. For example, here I've got some glue, or there is even some paint, which is a formulation, and ink inside your pen is as well a formulation. I've not included every single formulation. There are others, for example, medicines like tablets are often formulation, and even fuels, things like petrol, diesel, are often different mixtures of hydrocarbons, and they're in a formulation as well. Now, I'll just give an example of one of these formulations and talk why it's really important that we control the amount of the different chemicals inside. For example, paint down here. Now, paint is a liquid, but we want that paint to dry out. So it's really important that we have the right ratio of binder, which is what holds the paint together and helps it to dry, and the solvent, which gives it the liquid quality so that it can be painted on. Now, if I change the amount of either of these, then paint doesn't have that distinctive quality that we want it to have. We want it to be able to be spread on the wall, but then we also want it to dry out. There is also other things inside paint, for example, pigment, which gives it the colour, and it's really important that we have this in the correct amount as well. Now, because we are dealing with mixtures in this topic, I just thought it would be a really good stage of the video to point out how you can see whether you have a mixture or whether you have a pure substance. And it's really important to know what pure means in chemistry. In chemistry, pure just means only made of one substance. Now, you can test whether you have a pure substance by looking at a heating curve or a cooling curve. So if you have your pure substance and you're heating it up, it will melt at a clear point and then its temperature will increase again. However, if you have a mixture, you'll get a different type of heating curve. You will have no real clear melting point. It'll kind of look like this. And the reason for that is you've got different substances in there and all of them have different melting points. It is really important as well to get the fact that in chemistry, the definition of pure might be different to the definition of pure in everyday life. For example, you might say pure water in everyday life. However, that water has lots of different things added to it, and therefore it's not the same as pure in chemistry, where we mean it's only water inside there. The first method that we're going to look at for identifying the different substances that are inside a formulation or a mixture is chromatography. Now, chromatography involves using a solvent as your mobile phase and using paper as a stationary phase. And what we're going to do is we're going to place that mixture on the baseline. Now, chromatography works on the principle that different components inside a mixture have different solubilities. So when I place my mixture on my baseline and I put my chromatography paper in water, my solvent doesn't have to be water, but in this case I'm going to choose water as my solvent. When that water rises up, things that are more soluble in water will travel higher in the solvent, and things that are less soluble will stay towards the bottom of my chromatography paper. Let's write a little method on how to carry out the chromatography, and then we'll look at how we can actually use our chromatography to decide what is inside our mixture. So the first thing that you're going to do in a chromatography is draw the baseline in pencil. Now it's really important that you use pencil as your method of drawing your baseline, because if you use pen, that would be soluble and that would travel up your chromatography paper as well. So it's really important that that baseline is drawn in pencil. After we've drawn our baseline in pencil, what we're going to then do is place our mixture on our baseline. What we're then going to do is we're going to lower the chromatography into the solvent. We're going to lower the chromatography paper, into the solvent. And we're going to leave this until the solvent has travelled around about 3/4 of the length of the chromatography paper. So now what we can do is we can measure the distance that the solvent has travelled. So what we do is we measure the distance from the baseline to the solvent using a ruler. We call this line where the solvent has travelled up to, that's called the solvent front. Now what we're going to do is we're going to calculate the RF values of these spots. Now the RF values are going to be really important in determining what we actually have inside our mixture, because there'll be published values for these RF in different books and online as well. You can find out the RF value of different components in different solvents. So what we're going to do is we're going to measure the distance each spot has travelled. And we're going to then work out the RF values. And the equation for RF values, and this is the 6th step, we're going to work out the RF, which equals the distance moved by the spot over the distance moved by the solvent. And then finally, what we can do is we can take these values and we can compare them with published values. And this will tell me what is actually inside my mixture. So let's have a look at this chromatogram and work out what the RF value would be for our 2 spots here. So we've got our baseline here at 0 centimeters, and we've got our solvent front, and we can measure this to the nearest millimeter. It's gone up 40 millimeters. So the distance moved by solvent is 40 millimeters. Now I'm going to call the purple spot A, and I'm going to call the blue spot B, just to make it a little bit easier, because we're going to work out 2 RF values. So the RF value of spot A equals the distance moved by the spot divided by the distance moved by the solvent, and we take our measurements from the center of our spot. So if I go across here, it's reading just there 1, 2, 3, that's 13 millimeters. So to find out the RF value, what we'd do is 13 millimeters divided by 40 millimeters, and that'll give me the RF value of spot A. And let's do it for spot B as well at the same time. So the RF of this spot is, this time it's traveled up here and it's gone 25 millimeters. So 25 millimeters divided by 40 millimeters. And let's work out the RF values now on our calculator. And you'll always know that you've got these right because it should always be less than 1. If you've got a value bigger than 1, you know you've done it wrong. You've probably got them the wrong way round. And underneath the value is 0.625. So like I said earlier, these RF values are published in books and online, so I could then check my RF values of 0.325 and go on my solvent, which could be water, and find out what is inside my ink or paint or whatever mixture that I put on that baseline. Now, a lot of people in my class, when they were doing this, went, well, sir, my spots travelled up a different distance. How does that work? Well, that's because of the fact that people, when they're doing chromatography, they often don't leave it for exactly the same amount of time, so the solvent can travel up different amounts. However, the RF value should stay the same. For example, here, if I'm looking at spot A here, and the solvent didn't travel 40 millimeters, it traveled this time 50 millimeters. Well, I could actually work out how far that spot A probably traveled on their chromatogram by just rearranging the equation. Spot A has an RF value of 0.325, and if they left it and it didn't go up 40 millimeters, but this time it went up something like 45 millimeters, then I can tell you how much that spot should have gone up on their chromatogram as well by just simply rearranging that equation, and it would have gone up around 14.6 millimeters on their chromatogram. What we're going to look at now is a specific type of finding out in a laboratory what gas is present. So we're going to look at 4 gas tests. Now, this is some of my favourite practicals to actually carry out in the lab, so I do have a bit of a soft spot for these practicals, and we'll start off with hydrogen, probably the most famous of all the gas tests. Now, the reason why I'm going through these in maybe a bit more detail is because of the fact people do lose marks by not being specific in their exam. And the reason is, when we're doing these gas tests, it will want to know 2 things. It will want to know what you do to test for it and what the result of that test is. And you need to get these the right way around. So for hydrogen, what you do is you place a lit splint inside your test tube, and the result of this test is you get a squeaky pop. What about another gas? Well, these are all colourless, odourless gases really, and oxygen's the next one. And the test for oxygen is, this time we don't use a lit splint, we use a glowing splint. And what happens to the splint? The splint relights, just like the song, "Relight my fire." It relights. After oxygen, we're going to have a look at carbon dioxide, and the test for carbon dioxide is we bubble it through lime water. And what the result of that is the lime water goes cloudy. The reason for that is you're actually making a precipitate, which we'll have a look at later in the video if you are doing triple science. And then the final gas test that you need to know about is chlorine. And this one's mean because you have to use the correct words at each stage. So for the test for chlorine, you have to say damp blue litmus paper. And for the result, you need to say that it bleaches white. If you are studying combined science, you have finished today's video. If you're doing triple science, then we just have a little bit more to go through. So now what we're going to do is we're going to look at the way to identify different metal ions that might be present in a compound or a mixture. So the way to do a flame test to identify metal ions is first we need to clean our nichrome wire. So what you're going to do is you're going to dip your nichrome wire into some hydrochloric acid. And you're going to place this into a roaring flame. So now your nichrome wire is clean. What we can do is we can place a sample in the nichrome wire. Now this sample could be a solid, it could be a liquid, it doesn't really matter. You can sometimes dissolve your solid in a liquid as well. That's sometimes what people do in order to just get it to go onto the nichrome wire better. So now we've got our sample on our nichrome wire. We're going to place the wire into a roaring flame and observe the colour. Now, depending on what metal ion is present, it will depend on what metal is there. So, if my compound contains the metal ion lithium, what I should observe is I should observe a crimson colour. Now you have to use these words in your GCSE. Make sure you're using lithium is crimson. Next up we have sodium, which produces a yellow flame. After sodium we have my favourite, which is potassium, which produces a lilac flame. After that we have copper, which produces a green flame, and that could be copper 1 or copper 2 plus. And then finally we have calcium, which produces a orange red flame. You'd get the mark if you put a brick red flame, that's fine as well. But I would use these because these are the ones that are published on the AQA specification. So these are the words that I would use for each flame test. Now, sometimes we opt not to do a flame test. Sometimes metals don't give off a bright colour when you heat them up in a flame, or the fact that there's multiple metals in there and you can get what's called colour masking, which basically means there's so many metals in there that all the different colours being produced, they don't really show up, and we call this masking of colours. So the way to identify what would be inside this is by adding sodium hydroxide and looking at the colour of the precipitate produced. So we need to know some different colours of precipitates for different metal ions. The first one is aluminium, which is a 3 plus ion, and aluminium, actually calcium and magnesium, these all produce white precipitates. Now you might say, well, then how do you identify them? And that's a good question. So the difference is that when added in excess, that when you add sodium hydroxide in excess, I should say, the white precipitate will dissolve for aluminium. You can see one of them's actually in this picture over here. This precipitate over here, this beautiful one, is copper 2 plus, and copper 2 plus makes a blue precipitate. And the next one that I'm going to say, I'm going to actually give two in one, and this is for iron. The reason why I'm going to do this is because iron is a transition metal, and there is actually two ions that you can make. The first is iron 3 plus, which makes a brown precipitate. And over here, I actually do have an image of iron 2 plus. Iron 2 plus makes a green precipitate. Now you might be saying, well, how does it make two different colours? Well, this is because iron is, remember, a transition metal, so it can make ions with different oxidation states. So here, if I have a compound with iron 2+, we'll end up with a green precipitate. However, if it's iron 3+, we'll end up with a brown precipitate. Now, I think the best thing to do with these is get them all on flashcards and just test yourself on them. I think chemical analysis is one of them topics which is definitely a flashcard heavy topic. You can get them all on and get revising them. So I had a look at how to test for our positive metal ions, but how do we test for our negative ions? And the first one we're going to look at is if we have a halide present. So I'm just going to use x minus 1 for our halides, and we're going to look at 3 particular halides. We're going to look at fluoride, chloride, and bromide, and we'll look at how to test for them. So what we'll have is we'll have a metal halide. For example, we could have sodium chloride. That's a nice easy one to start with. And what we're going to do to test for it is we're going to add some silver nitrate. Now, when you do this, what happens is you make a silver halide. So this time it would be silver chloride, and I'll also make some sodium nitrate. So let's do my sodium nitrate, which would be NaNO3, and I'll make my silver chloride, AgCl, and this silver halide, this makes a precipitate. So that's a solid that will be suspended in that silver nitrate solution, and we'll be able to see this. So silver halides are coloured, and I actually have the 3 colours of the different silver halides over here. So if I have my chloride solution, then I end up with a white precipitate. If I have my bromide ion, then that will be a cream precipitate. And if I have iodide, that makes a yellow precipitate. Now, it doesn't matter what metal ion is. With my halide, it could be absolutely anything that we're going for here. So that doesn't matter. What matters is the halide that's present for the colour of the precipitate that you get. Now, it might also ask for your reagents for the halide test, and we've got silver nitrate as one of them, but also it will want to say that you want to acidify your reaction as well. The reason why we do this is to get rid of any impurities, for example, if there's a carbonate present in there as well. So what we do is we add nitric acid as well as our silver nitrate. The reason why we use nitric acid and not something like sulfuric acid is because of the fact that would then add sulfate ions, which will be another ion that we'll look at to test for. And if I added hydrochloric acid, well, that contains that chloride ion, so you'd end up with a white precipitate even if you had bromide or iodide present. So here again, what I would do is I'd get this on a flashcard, your reagents, your halide tests, and nitric acid and silver nitrate, and the colours of them precipitates. For iodide it's yellow, bromide it's cream, and chloride is white. Another negative ion you can test for are carbonates. And carbonates are CO3 2-. Now, the way to test for a carbonate is you would add hydrochloric acid. So let's just have a look at what that would look like. Let's just pick a random carbonate. Here I've got potassium carbonate, and I'm adding my hydrochloric acid. When I do this and I've got a metal carbonate and I add my acid, I make 3 products. I'm going to make carbon dioxide, water, and I'm also going to make my salt, which will be potassium chloride in this instance. Ooh. If I'm looking to balance this equation, well, on this side of my equation, I've got 2 potassiums. On this side, I've only got 1, so if I put 2 there, and now I've got 2 chlorines on this side of my reaction, but only 1 over here, so if I put 2 there, that should be balanced now, and I'll just check, just looking at it. Yeah, that's a balanced equation. And let's have a look at what this reaction would look like. So I start off with my solid potassium carbonate, or it could be aqueous, it doesn't really matter. And I'll have aqueous hydrochloric acid, and I'll make a gas of carbon dioxide, and that's important, as well as a liquid of water, and potassium chloride, which would be a salt, which will dissolve. So how could I use this to work out that I've got a carbonate present? You might have figured it out. It's the fact that you make this carbon dioxide gas. And we looked earlier in the fact we could test for carbon dioxide by bubbling it through lime water. And if we get carbon dioxide, we will end up with it going cloudy. You'll get a cloudy precipitate. You don't even really need to add hydrochloric acid as your reagent. It could be any acid. So for reagents, you can just put acid, but I always give a type of acid when I say it. If it asks for the reagents, I would say hydrochloric acid, but you could use any acid as your reagent. But I'll just put in brackets, I would use HCl. And visually what you'd observe is bubbling, and you could test that that's carbon dioxide by bubbling it through lime water and observing that cloudy precipitate. The last negative ion that we're going to test for is for sulfates. And sulfates we test for by adding barium chloride. That's our reagent. We also want to acidify it as well in order to get rid of any carbonates if they're present as well. So we could add a acid again. Don't add sulfuric acid because that would contain the sulfate ion. Remember, sulfates are SO4 2 minus. So I could add hydrochloric acid, and I'll just put that in brackets. I just want to add that as a note. The reason why we do this is to remove any impurities, mainly carbonates. So what happens when I add barium chloride to a sulfate containing compound is I make a white precipitate of barium sulfate. I'll just do a quick ionic equation just to symbolize it because we've not looked at them in a while. This would be the ionic equation for this reaction, barium plus sulfate, and they'll both be aqueous. And when they're added together, it makes the solid barium sulfate, and that is a white precipitate. Now, the techniques that we've looked at so far for identifying what ions are present inside a compound, they've all been laboratory-based techniques. What we're going to look at now is we're going to look at using instrumental analysis. Now, the reasons for doing this is because it's often more fast or quicker. We often need less of the sample, and it's often way more accurate. So what are some examples of instrumental analysis? Well, we could use flame emission spectroscopy, and we'll look at that one in a bit more depth in a second. We could use what's called mass spectroscopy, or we could use something like infrared spectroscopy as well. So I said we'd talk about flame emission spectroscopy in a bit more detail. Now, how this works is basically when you burn different substances, they emit certain wavelengths of light. Just as we saw with the metal ions earlier, they emitted colour. Now, the reason why that happens is the electrons, if we imagine an atom looking like this, what happens is the electrons get excited when you heat them up, and when they fall back down, they emit wavelengths of light. Now, when they're doing this, this can be recorded, and you can end up with a flame emission spectroscopy, which looks a little bit like something over here, where each element has different spectral lines, and you can work out which elements you've got by looking at them spectral lines. And this, of course, has the advantage over traditionally the laboratory technique, because you might have multiple different metals in a mixture, and therefore there might be lots of different spectral lines. So if you were doing just a normal flame test, they'd mask each other out, whereas using flame emission spectroscopy, you could match them spectral lines. For example, you could get a spectrum that looks a little bit like this. It would be produced like, and you get these lines coming out. And this is just an example, I'm just making this one up. That could be your spectroscopy that's produced, and then what you'd do is you'd go away and you'd find out what the spectrums of the different metals are, and you'd match them up. For example, these two lines here and this, that could be sodium. And there could be another metal in there as well, and we'll just have a look. I'll draw another one. It could be that it has a bit of lithium in there as well, and lithium might correspond to these two lines, and this one here, and this one here, and that would be a mixture of lithium and sodium present inside my mixture. Now, that is everything for today's video. I just want to say thank you for sticking around to the end of the video, and remember, if you did like it, to drop a like on it and subscribe to the channel.